Okay, so circles. We've studied circles before in mathematics, clearly. We're going to study them a little more from an analytical coordinate plane perspective here, in conjunction also with viewing a circle as a conic section. Take a cone, and if you make a slice parallel to the base and hold up what you've got, you'll have a circle. So a circle is considered a conic section. Let's start with a circle, say, whose center is at 0, 0 and has a certain radius r. In general, let's call a point on the circle x comma y. Well, the definition of a circle is it's a set of all points in a plane equidistant from a given point called the center. So if I set up a distance formula here, that distance from a random point xy to 0, 0, that distance will be the square root of x minus 0 squared plus y minus 0 squared. That has to equal r. And if I square both sides, I get r squared equals x squared plus y squared. And indeed, that's my general formula for an equation of a circle centered at the origin with a radius of r. Now, thinking back on what we can do with any graph in general, we can certainly do with a specific graph of a circle. So if I wanted to take a circle that has a radius of 13 and center of 0, 0, if I want to translate it left 7 units, I would replace that x with x plus 7, move it up 11 units, replace y with y minus 11. So this circle will be congruent to, same size as a circle centered at 0, 0 with a radius of 13, but I will have moved it left 7 units and up 11 units. So my center now will be negative 7, comma 11. My radius is still 13. So sometimes it's not quite so obvious to be able to read the coordinates of the center and the radius off of an equation that you're told is the equation of a circle. Here I'm giving you x squared minus 3x plus y squared minus 6y equals 13. I don't see a nice x minus a squared plus y minus k squared equals r squared. I'm missing some constants on this side. I've got, what am I going to do here? And thinking back on earlier in the year, we completed the square for a different reason earlier in the year when we were trying to do things with parabolas, finding vertices. We're also going to complete the square here on x and complete the square on y in order to find the coordinates for the center of this circle. So, in order to complete the square, I suggest you organize your work. X squared minus 3x, and then you got a y squared minus 6y, and you got your 13. What do I need to add to complete the square for the x stuff? I take half the coefficient of the linear term, square it, and add it. And I'm going to do that actually in writing. So that would be negative 3 over 2 quantity squared. And I can't just do that on one side. I would have to go ahead and also add it on the other side, negative 3 over 2 quantity squared. How about for the y's? I would take half the coefficient of the linear term, which would be negative 6 over 2 quantity squared. And I've got to add that as well onto the other side. That's negative 3 quantity squared. So go ahead now. This is then going to factor to x minus 3 halves quantity squared plus y minus 3 quantity squared equals, well, I have my 13, and then I've got plus a 9/4 and plus a 9. So now go ahead. Can we read off the coordinates of our center here? Our center is going to be at 3 halves, comma 3, because this reflects, remember, moving to the right 3 halves units, up 3 units. So I've taken that circle center at 0, 0, moved it right 3 halves, up 3 units, and my radius would simply be the square root of 13 plus 9/4 plus 9. And I'll let you do that arithmetic on your own. So how about graphing a circle with your graphing calculator? Circles are pretty easy to graph. I mean, if I give you a circle in center radius form, you know your center here is 3 comma negative 5 and your radius is root 5. Pretty simple to go graph that. You don't really need a graphing calculator to do that. However, good practice to think about when we take the square root of something, what needs to happen. If I want to graph this, obviously I could try and solve this for y. And A circle, remember, if I get a circle, a circle's not a function, it's a relation, because for an x value, I might have two y outputs. So I know that when I try and solve this for y, I'm going to get something, I'm not going to just get a y equals. I'm going to get two, I should be getting two y values. So go ahead and solve this for y. I can do that by saying y plus 5 quantity squared, move the x minus 3 squared over to the other side, equals 5 minus x minus 3 quantity squared. And when you take the square root of two sides of an equation, you need to make sure you take a plus or minus on one. You say, aha, there's where my two y values are going to come into play. And solve for y, I get y equals, I get y equals negative 5 plus or minus the square root of 5 minus x minus 3 quantity squared. So what can I do then to graph this? Well, into y1, you put negative 5 plus that square root. Into y2, you put negative 5 minus that square root. And what that's going to do is give you both the top half and the bottom half of your circle. So try it out on your calculator. Okay, last but not least, another type of problem you might want to do with circles. Example of a problem, suppose we want to find the intersection of a line and a circle. Now, do a line and a circle always intersect? Clearly not. You can have a line and a circle in a plane and they don't intersect. How could they intersect? Well, they could intersect in 2 points, as I've shown here, or they could intersect, suppose I have a line tangent to a circle, the intersection would be 1 point, or indeed there are lots of lines that would not intersect a circle, given circle at all. So the strategy is, if you've got the equation of a circle and equation of a line, I have two equations and two unknowns, and I'm going to use substitution to get the job done to find out the intersection points. So for this specific problem, 3y plus x equals 6, x squared plus y squared equals 10, I can quickly set up a picture of that. Root 10 will be my radius of my circle. That's about 3 point something. Let's call it 3.2. I can find x and y intercepts here for the for my linear equation. Y is 2 and x is 6. Look at those those intercepts, and then note that I'm going to get two. I should be coming up with two solutions, two intersection points for this specific line with this specific circle. So let's see what happens. So go ahead and solve your linear equation for one of the two variables, and it doesn't make any difference. In this case, it looks pretty simple to solve for x. X is going to be 6 minus 3y. Go ahead and then take that and plug that into your circle's equation, and then you'll get an equation with one variable. So I would get 6 minus 3y quantity squared plus y squared equals 10. Solve for y. 36 minus 36y plus 9y squared plus y squared equals 10. Let's see, like terms and whatnot. 10y squared minus 36y. Bring the 10 over, plus 26 equals 0. Go ahead, factor out a 2. 5y squared minus 18y plus 13 equals 0. Then you can go ahead and factor that. Let's see what happens. Factors of 5y squared, 5y and y. Factors of 13, 1 and 13 are my only choices. Can I get an 18 out of that? Indeed I can. 13 and 5 gives me 18. I've got a minus and a plus, so that's going to be a minus equals 0. So at y equals 13 fifths and y equals 1, that's corresponding to my two intersection points. And then I simply want to see, plug those back into the linear equation to see what you get for your x coordinates. So as we were saying here, you want to plug your values, your y values, back in. You want to plug them into the linear case, just because if you plug them into the circle, you might get confused. You're going to get, for each of your y values, you get two x values, and those are going to be extraneous. So you want to make sure you plug back into your linear case. So 3, let's say 3 13 fifths plus x equals 6. You can solve that and get an x coordinate, and 3 times 1 plus x equals 6. Solve that, and you'll get your other x coordinate.